So it's my pleasure to introduce this new track 1 for the second day of the workshop. And we're gonna have Ryan Tanaka from USC ISI and Steve Jacobs from Battelle Neon talking about end-to-end workflow execution and monitoring and Neon back there. Ryan, the floor is all yours.
Great, thanks, Raphael. So hello, everyone. Thank you for joining. So this talk, as Raphael said, is titled End-to-End Workflow Management and Execution. And I'll be talking about the Pegasus Workflow Management System that we've been developing here at ISI. So first and foremost, Pegasus, it's a workflow management system, and it's used for executing large-scale, computationally intensive scientific workflows. This software system helps to bridge the scientific domain and execution environments by mapping high-level workflow descriptions onto distributed resources. So this is useful for scientists because this enables them to automate their work as portable workflows, so they can write these abstract workflows using our API and then run that same workflow on different types of execution environments, because over time their workflow might stay the same, but the execution environment might change. And so these workflows are sort of portable in that sense. Also, it enables scientists to recover from any failures that occur at runtime, thanks to some fault tolerance mechanisms that we've developed, such as checkpointing and data reuse. And then also, scientists are able to debug their failures that occur in their computations, which is very useful for large workflows. If something fails, we provide command line tools as well as web-based tools that these scientists can look at their workflows with. So Pegasus is built on top of HT Condor, which is been a proven workhorse in the distributed high throughput computing domain. And so we really leverage the low level execution functionalities that it offers. So we really use HT Condor Dagman and HT Condor SCED-D. So with that brief introduction to Pegasus, I'll be going over some of its basic concepts. So workflows are multi-step computational graphs that are organized as directed acyclic graphs. And to define an abstract workflow, you would use one of our Python, Java, or R APIs. These workflows are abstract in the sense that users don't need to map jobs onto physical resources or create any jobs relating to file transfers of input and output files that these jobs use or produce. Then Pegasus will also plan this abstract workflow into an executable workflow, which is something I'll go over in a bit. So let's say, for example, that you have this workflow here on the right. We have this job. So here, the boxes represent input and output files. These ovals represent jobs, and then these arrows represent dependencies between these jobs. So the workflow starts with this initial input file, then it has this job preprocessed, produces these two files, and so on and so forth until you have this final job called analyze that then produces a final output file, which is like the result that you would want as a scientist from your workflow. So what does it look like when you use, let's say, a Python API to develop a workflow just like this? So the first thing that you do is define the initial input file to the workflow, and you would specify where this resides, so an absolute path, and what machine that this resides on. So in this case, local just represents your submit host. And then the next step is that you would define any executables. So in Pegasus, we call these transformations, but they're essentially executables. So you define any executables that are used within the workflow. So if you look over here, this workflow contains 4 jobs, but we've only defined 3 executables. And that's because throughout the workflow, you might reuse an executable for multiple jobs. So for example, find range 1 and find range 2 here, they're going to use the same executable. However, when they run as part of a job, they'll be passed different command line arguments and use different input and output files. So we just have this to separate jobs from executables. And also, it's important to note at this step, you can also specify any containers that your jobs would run in. So we support Docker, Shifter, and Singularity. So once you've defined those things, you can begin building up your workflow. So first you just define a workflow object like this, and then you start defining the jobs that the workflow comprises of. So we have this job pre-process. It uses this executable that we defined in the previous slide. And when the job runs, it's going to run with these command line arguments right here. And the job requires that this file be present. So it's an input file when the job runs, FA right here. And the job will produce two output files, FB1 and FB2. And so you would continue this until you've defined all of the jobs that are in your workflow. Also note here that these dependencies between the jobs they're automatically inferred by Pegasus based on job input and output files. However, if you want, you can manually add them. So the next step after you've defined your abstract workflow is where Pegasus really takes over. So the workflow will go through this planning process. And a number of things can happen during this phase. So first, there's a data reuse module that might optionally prune jobs for which output files already exist. So like in this example, we have this workflow that we just built up. And let's say that we've specified that, hey, this file already exists because maybe we've rerun the workflow, or we've run the workflow before. And we got to this point, or we just have this file. So Pegasus will prune that job from the workflow. And so this can sort of save some time in terms of computation and resource usage. Now, the next thing is that the user can specify some task clustering optimizations that might be performed. And this is good for small, sort of fine-grained independent jobs that you want to merge into a coarser-grained job. And this can be advantageous because you can avoid some of the queuing times associated with resource schedulers. And also, if your independent jobs happen to use the same input files, there's another advantage to that as well. In this example, like let's say we set up these two to be clustered, well, you end up with this right here. Then after that phase, there's this mapping onto physical compute resources. So in Pegasus, we have this notion of a site catalog, which is separate from your workflow. And this is where you sort of specify all of your physical resources. You'd have a Condor pool or a grid, and Pegasus looks at that and your abstract workflow and maps everything together. Also, auxiliary jobs for data staging, cleanup, and file registration, things like that, they're automatically added into the workflow. So after the workflow has gone through that task clustering optimizations, we get something like this. And then once jobs are mapped onto physical compute resources and these auxiliary jobs are added in, we end up with a workflow that looks like this, which is our executable workflow. And it's important to note that this transformation from this workflow to this workflow can be different depending on flags that you set when you're defining your abstract workflow using the API, and also depending on the execution environment that you're going to run this workflow on. So finally, this generated workflow, it's ready and it'll be submitted by Pegasus through HT Condor to be run. So now that I've gone over some of the basics of Pegasus, I do want to discuss some of its important features that it offers, which makes it useful to scientists. So Pegasus supports 3 different data staging configurations. First, we have HT Condor IO, and this is useful when you're running on HT Condor pools or the Open Science Grid, for example. And in this scenario, worker nodes don't share the same file system. Here, data is pulled from, pushed to a submit host via HT Condor file transfers. And then also the submit host is used as a staging site. Then there's the non-shared FS data staging configuration, which is useful for clouds and also Open Science Grid. So in this case, again, worker nodes do not share a file system, but data is pulled or pushed from a staging site that's possibly not co-located with the computation itself. And we also have an internal file transfer tool called pegasus-transfer, which handles all the file transfers in this setup, as opposed to HT Condor file transfers. And then there's the shared file system configuration, and this is used for HPC sites, Exceed, campus clusters. And in this scenario, I/O is done directly against the shared file system. So with these three data staging configurations, we can cover sort of a wide range of execution environments that researchers might want to run their workflows on. So as I mentioned, Pegasus Transfer, it's an internal file transfer utility that we've developed. It supports a number of different protocols that you can see here on the right. It also does directory creation, file removal, and it can handle two-stage transfers between incompatible protocols. So for example, if you want to do grid FTP to S3, it's simply executed as grid FTP to a local file and then that file to S3. Pegasus Transfer will also do parallel transfers. It has automatic retries set up, and you can configure the amount of times that the transfer will retry until it results in a failure. And then finally, it will do some credential management. So some of these protocols require credentials, and so Pegasus Transfer can handle that. Next, we have automatic integrity checking. So this is turned on by default, and this applies to both stageable executables and files. So for files that are like initial inputs to the workflow, the user can specify a checksum that applies to that file. And then for files that are produced throughout the workflow, so intermediate files, the checksums are generated and tracked throughout the system automatically. At any point in time, if the checksum validation fails, then the job will fail. So on the right here, we have sort of a simple example of what this looks like. We have this workflow, which is a pipeline of just two jobs, and takes in an input file, produces an output file, it's used by the next job, and then finally produces a final output file. So when this first job T1 runs on some compute site, it actually itself looks like a little workflow. And what happens here is first, this input file is staged in because it needs to be there for the job. Then checksum validation happens, so we make sure that the checksum for the file is okay. Then the job runs, the job produces an output file, and then Pegasus will compute the checksum of that output file and keep track of it. Then that file is staged out so that it can be used for the next job, T2. So when T2 runs, similar process happens. Again, the job itself looks like a small workflow here. Now, one of the concerns here was impact on performance when we did this. However, in practice, we did find that the overall impact on computational time was very low. It was around 0.07%. And you could say that larger files means paying more for computing that checksum, but it also does mean that your jobs are likely to last longer as well as your file sizes increase. And so therefore, the overall impact on computation time is still very small. And again, so this feature is for those who would like to take advantage of it, and we do encourage people to use it because these little errors can occur in your data and you might not even notice, but otherwise it can be turned off. So part of what makes Pegasus useful to our users is the monitoring and debugging tools that are offered. So for example, we have these three command line tools. There's Pegasus Status, Pegasus Analyzer, and Pegasus Statistics. With Pegasus Status, it's very useful for viewing the current status of a running workflow because you can view a summary of jobs. And if you've written a hierarchical workflow as well, you can see the status of all of these sub workflows that are running as part of that root workflow. So on the right, this is the output of Pegasus Status. We can see a summary of some jobs here. I had to cut it off over here, but yeah, and it shows the sub workflows that are running, the root workflow, and then a total summary of everything that's going on. So this is useful when you submit a workflow and you just want to check up on it to see how it's doing. You could just call Pegasus Status. Then we have Pegasus Analyzer, which is very good for viewing errors that occur for any of your failed jobs. So let's say you have an executable that runs part of a job and it throws a runtime error, and you want to see what that error is. If you call Pegasus Analyzer, then you can see, for example, standard error from that job. And then you can go and debug your job appropriately. Then we have Pegasus Statistics, which is useful for viewing a summary of the workflow after it has finished running. So it'll show things like succeeded number of jobs, failed jobs, retries, workflow wall time, and also any integrity verification attempts and failures as well. So in addition to the CLI tools, Pegasus does have its own dashboard that you can spin up to get a more graphical and interactive view of what's going on with the workflow. And so these two images are just one of the many views that you can get into the workflow if you are using the dashboard. And then finally, we have the option of setting up custom monitoring solutions. So Pegasus can be figured to send workflow execution events to an AMQP endpoint, such as a message queue, and then you can handle the data from there however you see fit. So here, this is like a typical Pegasus setup where we have it running on a submit host, and we have Pegasus monitor-d running, which is just one of its processes that runs. And then it's connected to a Condor pool. And as your jobs execute on this Condor pool, monitor-d will create a workflow execution event, and that event will be sent over to whatever endpoint that you've configured. So in production, this is what our own data collection setup looks like. We have a RabbitMQ instance, so that's the AMQP endpoint here. And then from there, we have a service called Logstash that runs and collects these events from the message queue as they appear. And it inserts them into certain indexes in Elasticsearch. So we have like a 2-node cluster that we're running, and that's where all the data gets stored. So once that happens, the data is then available through 2 web services. There's Kibana, which is useful for looking at specific workflow events or doing any type of, you can do text search very well. You can filter all jobs for a specific workflow and do text search on maybe all of the standard out from all of those jobs if you want. And then also you can view this data as a dashboard through a Grafana instance. So you just open up your browser and you go to the URL that we have set up, and you can view a dashboard that looks just like this. So this is good for viewing either a collection of workflows. You can see how many jobs were run, how many workflows were run, cumulative wall time, failures, and all those things. But you can also drill down to a specific workflow if you wanted to look just at that. So then the final feature that I want to go over is the Pegasus Ensemble Manager. So this is a service that we've developed for managing collections of workflows that we call ensembles. And so this is good when you have tens or hundreds of similar workflows to run, and you want to sort of manage them instead of just manually submitting each of them. This way you can submit all of them through the Ensemble Manager and sort of query them by the ensemble that they belong to. It also allows for throttling of the concurrent number of planning and running workflows. So if you want to sort of limit the amount of workflows that are currently running, you can do that as well. Like if you have 100 and you only want 10 to be running at the same time, you can use this for that. And also the Ensemble Manager supports triggering of new workflow runs based on the arrival of input files, which may match one or more given file patterns. So Pegasus is sort of a task-driven workflow management system, but with this functionality, we do want to offer more of a data-driven approach for different types of workflow runs. So let's say that you have some data source that's uploading or downloading text and CSV files to some directory, where you can set up a trigger using the Ensemble Manager that will, at a given interval, let's say an hour, look at this directory, collect all the new files that arrived within that interval, and then kick off a workflow as part of that ensemble. So that's what that would look like here. So it's kind of a way of making workflows dynamic in a sense. So I'd like to conclude with some examples of how Pegasus has been used in production. So LIGO is the Laser Interferometer Gravitational Wave Observatory, and it's a facility for gravitational wave research, which, as its name suggests. And some of the work that they do involves using a software package called PyCBC and they run Pegasus workflows that use the PyCVC program, and they run it on Open Science Grid and Exceed. And so like this image on the right here shows, it's from some of their past work where they've seen what two black holes look like when they're about to collide. And so the science that they're doing here is like very serious, very compute intensive. So what do these workflows actually look like? So a typical PyCVC workflow can have upwards of 40,000 compute tasks, 1,100 input files, produce 63 output files, and all in all process 725 gigabytes of data. And typically it's run on the LIGO data grid, which is their in-house setup, and then also Open Science Grid, EGI, and Exceed. And this image on the right here shows like what the typical structure or topology of their workflows look like. So the plots that I have here on the right, these are plots that are typically generated as part of a post PyCVC workflow analysis process. And so these plots, you know, it's not part of Pegasus, it's just part of PyCVC. And these are just aggregations of metrics that are collected from the PyCVC application that are used to evaluate its performance. And so part of our recent work with LIGO and also Syracuse University involved using the AMQP data collection setup that I previously mentioned to improve monitoring capabilities of these PyCVC workflow runs for LIGO researchers. And so what we did was set up a dashboard using Grafana, which is similar to the one that we have for our own use, but with some custom features to it. And it will generate these 3 plots in real time as the workflows are running. And so we're able to do this because Pegasus not only sends workflow events to an AMQP endpoint, but it also, like any application-specific metadata that's parsed by Pegasus will be sent as well. So if you're writing an application and you want to run it as part of a Pegasus workflow, you can output the data in sort of a specific format that Pegasus recognizes, and then that data will be sent as part of the workflow event. So you can sort of get data collection almost for free. And so finally, in summary, over the last 12 months, we've seen Pegasus users have ran upwards of 240,000 workflows, that comprising of, you know, around 145 million jobs. And these workflows do encompass a variety of scientific domains from physics, which is this one right here, seismology, which is this one right here, and epigenomics. And that's just to name a few. And so as you can see from these images, you know, we have encountered a wide variety of workflow structures across these domains. And it's really interesting to see, you know, what everyone's workflows look like. You know, some are small, some are large, some have many tasks, and some have this sort of fork join topology. And so, yeah, that's been really interesting to work on. So with that, this concludes this presentation. And if you would like to know more about Pegasus, we do hold regular office hours, and you can connect with us through these links right over here. And that's it. Yeah.
Thank you.
So in the second part now of this presentation, I'm going to have Steve Jacobs from Bethel Neon. Steve, are you able to share your screen?
Getting it set up right now.
Okay.
Yes, and in the meantime, if there are questions for Ryan, people can pose them, I guess, by voice or in the chat.
Is that coming through?
No, are you sharing your screen?
Yes.
No. Yes, great.
There we go. Okay. Hi, I'm Steve Jacobs. I'm at the NEON program with Battelle. This set of slides was adapted off of a bunch of material for some other folks, so had them listed up in here. For those who don't know what NEON is a ecological observatory spread out across the continental United States, Puerto Rico, Hawaii, and Alaska. We have 81 field sites, 47 terrestrial and 34 aquatic. We do all kinds of different data collection at these sites. There's a flux tower that has lots of atmospheric measurement sensors on them, soil sensors. We have scientists in the field that collect observational data and samples. There's an airborne remote sensing platform. We have similar instruments in lakes, streams, rivers, there's groundwater wells, and all those sorts of things. The pipelines we're talking about right now are dealing with the sensor instrumentation in the terrestrial and aquatic sites. Let's go through too many animations in here. So the existing processing system that we have at NEON is running in a piece of software called Apache Airflow, which is an ETL workflow tool. It models DAG similar to what Ryan was showing earlier, but it's also date-based. Because we collect data at NEON and basically do QA/QC processing and reformatting, we don't sort of need this on-demand simulation submission sort of system. We need to process data every day as it comes in. And it provides very good visibility and operational tooling. You can see what's going on with the built-in tooling. You can easily rerun data. It provides performance metrics around what is going on in the system. This is just a screenshot of the web UI. And you can see here at the top, there's days of data. And then there's sort of this tree model that shows all the dependencies between the pieces in the DAG. And there's also graph views of this and things too. You can go through and see each individual piece of the execution and what's happened with it. In addition, if you click any one of these things, you have options you can do for individual steps of the process. So you can rerun one individual step. You can have it clear the state for everything that's downstream of that step recursively, in the future, in the past, look at logs, all this sort of stuff. And I apologize for all the animations popping into here, but I didn't think they were in here. The system was derived from a legacy code base that's written in Java. It was originally run on an HPC scheduler that didn't have any sort of data awareness in the way that it was built. And so we ported it over to Airflow to make it possible to see what was going on with the system. And the tooling that's in Airflow allows us to reprocess. So if some data was missing for a site because it went offline, we can go back in and reprocess data for that site by going in specifically to the day in the interface and clearing it, or writing a script that goes through and does it. But it doesn't automatically reprocess. And all the software we're running, there's a lot of internal data services that code needs to talk to be able to get data that needs to run through the process. And so the inability of this system to rerun when in response to change is starting to become a large operational overhead. It's just lots of labor in order to actually reprocess these things. So we're looking for a different way of processing this, and we ended up, enumerating all the reasons why we wanted to move to this. The dynamic data was the largest driver. We continuously receive new data, and sometimes the data that we get from a site will be incomplete. If it goes offline, you're always going to have a partial day until it comes back online to catch up. All of the metadata associated with processing that sensor data, it can change as well. Thresholds can be adjusted by our science team. There can be new calibrations. Some of the aquatic instrumentation we have requires field calibrations every 2 weeks. And so every 2 weeks, there's a new refined set of calibrations coming in that need to be run against that data. And Airflow doesn't provide any sort of traceability about what software or what inputs created a set of outputs for us. So we want traceability on the data that we produce, and we want to be able to reproduce, to know that we can reproduce the results we've gotten from a piece of data. And another challenge for us is that we want to open source our code base that does all this processing, but the dependency on internal data services inside Neon's infrastructure makes it difficult to do that. And lastly, the way that this legacy code base was developed inside Neon, our science team would write what's called an algorithmic theoretical basis document that would describe the process they want the software to take to produce output. And then our software team would then go implement it. And usually along the way, the science team went and wrote some R code or went and wrote some other code to test that out anyway. And so we thought if we could have the cyber infrastructure team concentrate on all the sort of data flow components and how to access the data and how to get the data to where it needs to go, we could use our science team to do the algorithm development for the actual products. There we go. So Pachyderm is the system we ended up using for this. And the first, I'm going to skip through this because there's a lot more content coming up in here. I don't want to get too bogged down. But this is a picture of the DAG of the first prototype that was built. And Pachyderm is another DAG-based workflow tool. But one of the biggest difference between it and other tools that we looked at is that it can process, it can trigger the DAG in response to changing data. So in this picture, these little silos you see right here are file repositories. And these file repositories are versions, sort of like a Git repository. So you can do commits and branches and that sort of thing with the data. And when inputs change, Pachyderm will rerun pieces of the pipeline that need to be rerun. So every box here is what Pachyderm calls a pipeline. It's really just an execution step. Every pipeline can have any number of input repositories and creates one output repository, and you can chain things together like that. So in this diagram, at the end here for this platinum resistive thermometer that we're using for soil temperature, the inputs here are the calibration files and the PRT data that are coming into the pipeline. And over here off to the side is a repository of data that says what the location of all these sensors is. And then further down here is all the sort of constraint and threshold information that goes into the QA/QC algorithms. And this pipeline is sort of broken up into steps. There's this calibrated conversion that changes the PRT resistance measurement into a temperature reading that occurs here. And we don't need to know where that sensor is to do that sort of calibration. Then after the calibration step, location's brought in and the data sort of reorganized by location for these steps. And then that goes into sort of the QA/QC pipelines involving the thresholds. So data sort of cascades down there. So if a scientist adjusts a threshold, you know, let's say, whoops, the thresholds were supposed to be for Florida, but instead the thresholds for Alaska are in there for soil temperature, and they adjust it, then what will happen is just this piece of the pipeline will rerun in response to that change of data. So not the entire pipeline doesn't run, just the pieces that are changed. And this is a sample specification for how those pipeline specs are put together. Everything in Pachyderm runs on top of Kubernetes, and Kubernetes runs with containers. So you specify a Docker container that you want to run in your pipeline, and you can set environment variables. You have to set the input repositories that go into the pipeline, and then there's a file globbing pattern that determines how to match for input. And this is sort of a very important specification piece inside Pachyderm because it determines whether or not an entire directory of files will match, or subtree of files will match in a directory structure, or individual files. And Pachyderm traces the commit history all the way through this pipeline. So every single output repository gets a commit when a job runs, and you can actually trace the commits all the way through. It's confusing to look at right now, but they have a change coming that's going to unify the commit IDs all the way through the pipeline. So if you look at one commit ID, it'll be the same for every repository of data throughout the pipeline. Just gonna jump ahead here. The fact that Pachyderm runs with Docker containers, and the Docker containers that you build for the pipeline don't require any sort of Pachyderm agent or special API or anything in them. It just delivers files and runs an executable in the container for you. Means that we can release those containers publicly. So we've done that development on GitHub, and we're going to be opening that up to the public so they can get access to those containers. Like was in these slides, the trade-off on how many files you select is very important in terms of running Pachyderm. But I wanted to skip through some of this to get to some of this other content, because from my perspective, one of the hardest things that we had to accomplish here was to actually create files out of the data that Neon uses. Earlier, I was saying that we had this legacy Java code base that depended on these data services for accessing everything that it needed to do processing. Well, none of those things were files. They were all in a database somewhere. And Pachyderm is file-based processing and provenance tracking. So if you don't have files, you're not going to get any of that. So we went back with our engineering team to look at creating schemas for all of the various sensors that Neon has. I think there's 61 different schemas that have been put together at this point. But when we did this initial prototype, the first sensor we needed a schema for was the platinum resistance thermometer that we have. And I don't know if anyone's used the Neon site, but this is what a lot of our data products look like. There's this code that has, it's a Neon data product at this domain, at this site. It's a level 0 product. And these all have bearing on all kinds of information about, what type of thing is it reading, where is it located, and that sort of stuff. But you have to be able to come up with these names. Well, this part of the product, there's actually 4 different products that are all related to PRTs. Only one of these is used in soil. But what happens today is we receive some data, and then these names get attached when it comes in at ingest, and it's done by stream. Not like if we have a sensor that has 10 streams of data, there's 10 unique names for each one of these things, and they're all ingested separately. So these schemas got built in a format called Avro, which is an Apache project for a binary data serialization format that has a JSON delimited schema that describes what's going into the data. And so if we figured if we could get these things converted into Avro and we could start ingesting this as Avro as opposed to this legacy XML format, that we'd have a file format we could use inside Pachyderm. And this is what these schemas look like. The only problem is that when we started doing this with these Avro files inside of Pachyderm, we started noticing that we were getting a lot more processing than we thought should be happening. Pachyderm is only supposed to reprocess in response to change, and we were getting reprocessing all the time. Well, it turns out that Avro can be serialized 2 different ways. So if you're serializing it over, say, a messaging system like AMQP or Kafka or something like that, then you're using what's called Avro's record format. And the record format is just standalone serialized binary data with no schema attached that just has the data coming in. You have to have the schema to be able to decode it. But there's also a file format, and the file format embeds the schema. So you get the self-describing file format, which is nice. But it also turns out that they include this randomly generated 16-byte sync marker. So if you write the same data to the same file twice, you end up with 2 different checksums for the file, which doesn't work out so well inside Pachyderm. So we ended up discovering another file format called Parquet. Parquet's another Apache file format. all this stuff comes out of the Hadoop ecosystem of tools. But the big deal for Parquet for us to start with is that if you write the same data twice, you end up with the same file. So it works a lot better in Pachyderm for us. It turns out that the library support for Parquet is a lot better as well. There's this project called Apache Arrow that provides a really nice Python and R and C interface to Parquet files that we've been using. And it also turns out that some of the other features on Parquet are pretty nice as well. There's column-based compression. There's more native types supported, specifically unsigned types, which aren't available in Avro. And there's predicate pushdown support. So if you're searching for data, you can actually get to it more efficiently inside Parquet. We actually had written an R driver for Avro that has been submitted as a PR to the Apache project to do this. But another surprising benefit is just in terms of file size. You know, you can see here, this is 24 hours of data from one of our, this is a 3D accelerometer, I believe, called MTI 300, that we collect data from at 40 Hertz. This is just 24 hours of data. And, you know, gzip CSV is 243 megs. HDF with embedded, I think this was embedded zlib compression, is 372 megs. And as a Parquet file, it's 155 megs, which is great. It also turns out it's a lot easier for us to work with the data in these sorts of formats. This is how you would get data out of our system before. This is the type of query you'd have to do to get some values out. And the table structure didn't even tell you this was resistance, right? You're just expected to know that based on 200530001, which isn't very, very useful if you're trying to track this stuff down. And now you can just open up in Pandas and you get a data frame. And you just say, open the file. There you go. That's a 24-hour period of data. And this is just an example of one of those MTI files, which I think has 23 columns. Yeah, 3.6 million readings and 23 columns for one day. We also needed file formats for more than just the sensor data. The calibration cert files were already files, but that threshold information I talked about, you know, would have things like the min-max allowable values and different parameters for different quality checks. It's all in a database as well. And the location information that tracks the locations of sensors in the observatory over time also weren't in file formats. So we came up with some JSON formats for that. This is an example of some of the threshold information. We use GeoJSON for tracking the sensor locations, and this is just an example of that. I think that's it. Wow, that was fast. Okay. Are there any questions?
Thank you, Steve. Any questions for Steve or Ryan?
I had some other slides in here too with the DAG views from Airflow, and we also do metrics exporting with Grafana, similar to what Ryan was showing.
Yeah, so while people are typing questions, I have a quick question for you, Steve. Oh, actually there is one there for you. So I'll let you answer first and then I can ask mine later. There's one on the chat.
Oh, I don't know if I have a tree depth number, but the work that's happened, the question is, how big have your Pachyderm pipelines grown in terms of number of steps? Yeah, Cove, he's in here, he's been working on this. This is something like 35 to 40 steps. We have about 75% of the modules done that we think have like common components for all the different data products that we produce. I think we don't anticipate them getting too much longer than 35 to 40, maybe 50 for some of the ones that have been put together.
Okay, my question is more like related to the files you mentioned, because you said when the files change, you launch a new workflow, and each workflow that you are processing only process a unique set of files, or you reprocess some of the files you had before. So what is the dynamic behind that?
So in the pipeline specification, you remember the globbing pattern that was there?
Yep.
It depends on that globbing pattern. So if your globbing pattern is selecting individual files, then the workflow will only run with the individual files that you've uploaded. But if the workflow if the workflow specifies like an entire directory of data, let's say the data for a day, and you change just one file in that directory, it'll run with all the files that are in that directory in the current commit.
Okay, got it. There is another question from Chad. For those unfamiliar with the systems, Pegasus and Pachyderm, what level of effort is needed to get them set up for evaluation and production? So Ryan, do you want to take this one? And then Steve goes.
Yeah, sure. So for Pegasus, I think the biggest thing, excuse me, is that you need to install htcondor. And so if this is a local Condor pool, that can be pretty straightforward. I think when you have to run on a cluster, then you need to get htcondor installed there. So there could be some effort involved with that. And so, I guess it really depends on the execution environment that you're trying to run in. So for example, like for me to get Pegasus set up on my own machine with htcondor was pretty straightforward. However, if you do have like a larger setup with maybe some clouds and, a campus cluster, then it's not as simple. I guess maybe, yeah, that's kind of how it is. It depends on where you're trying to run the system.
I think sort of the answer is sort of similar for Pachyderm. Pachyderm itself is not particularly complicated, but it has some dependencies that are. So you have to have a Kubernetes instance in order to run Pachyderm. So if it's something you're trying to get up and running for development on your laptop, let's say, if you install Docker Desktop, it comes with Kubernetes built in. You just turn it on, and then you can use packctl against it and work with it. Or you can run something like Minikube, or even Kind, I think would work with it. But if you're going to run this in a production instance, you're going to need some sort of object storage to back in the repositories, and they support, I think, Azure and Google and S3. We're using S3, an S3 object storage system on premises that it works with. And you're going to need a Kubernetes cluster to run it in. And a lot of the complexity with Pachyderm is more Kubernetes complexity than it is Pachyderm complexity. So if you're trying to troubleshoot why something isn't working, you inevitably need to have some Kubernetes expertise to figure that out. And also in terms of sizing the cluster, what resources are needed, how much ephemeral storage do you need, all that sort of stuff is really a Kubernetes question more than it is a Pachyderm question. In terms of getting this ready for production use at Neon, I think the largest piece of understanding we've had to do with the people writing these workflows is Kubernetes resource restrictions. The way that the Kubernetes scheduler works and schedules resources is based on limits and requests. And so you need to be careful about making sure that you put an approximation of the CPU and memory usage that your job is going to need. Otherwise, the scheduler will naively put you somewhere that may not have enough resources. And then when you use them, it'll start killing jobs in the cluster to make more space so that your job continues to run. And that can cause all kinds of problems if you're not careful about that.
Yeah, so I just wanted to add one more thing, actually. If for Chad, if you did want to evaluate Pegasus, like not in a production standpoint, like you just wanted to see how it works, maybe write some workflows, submit them, then I just pasted a link in the chat here, but we have sort of an entire Pegasus development / execution environment that's in one container. And so you could spin that up, write your workflows, submit them as if you were running on sort of a larger setup and see how it feels from there. And then if you like it, then you could go ahead and try to get this running on a sort of larger infrastructure that you have.
One of the questions I actually had for Ryan was what his thoughts were on common workflow language or DVC or any of these sorts of workflow description pieces that are coming out.
Sure. So yeah, I actually don't know anything about the second one that you mentioned, but for common workflow language, we do have a converter that works with, I think it's version 1.1 of CWL. Now it works on a subset of CWL and not the entire language itself, because there are some things that don't map sort of directly from CWL into Pegasus workflows. But we do support it, and we can do the conversion for you. So for anyone here that does have CWO workflows, and if you would like to try to run, use them with Pegasus, we have a command line tool that can do the conversion for you. There might be a few things you might need to change, but we can help you with that as well, just to get it working.
Yeah, but Steve, another way to answer your question is that when we looked at CWL, our sense was that describing workflows in CWL is much harder compared to what we would do in our own task-based format, as in Pachyderm or in Pegasus. So it seems like because maybe they generalize the format too much, it's a steep learning curve to understand what the format is about in the first place.
DVC looks rather interesting to me in terms of its simplicity. My perspective with Pachyderm is that from an automation perspective, it's extremely valuable for what we're doing. But in terms of a workflow description tool, it's pretty simplistic. I mean, we don't have extremely complicated needs. And one of my worries going forward with these open source components that we're creating is giving the community of users the ability to run those workflows in sort of a standalone mode with a fixed set of data outside of our Pachyderm pipeline. Because there's nothing in the containers that constrains the use, right? Other than the intermediate artifacts and having access to them. And so having a way to stitch them together simplistically, like in a scripted run, I think would be really useful. So something like DVC might enable that. I don't know, we haven't really played around with it much. I saw, Robert, you had a question about that, those intermediate data pieces. So today, yes, Pachyderm has this idea of like input repositories, and then any type of repository that's output from a pipeline is sort of automatically created, and you can't commit files to it independently. It has to be committed there from the pipeline's run. And currently all those are stored in a object storage system. So what Pachyderm does today is they have an etcd instance they instantiate in your cluster that stores all the metadata about the objects, and then the actual blobs of storage get stored in object storage on the back end. But all the intermediate artifacts are stored. And this is something that's a concern for us in the future. Right now, most of the data we're dealing with is pretty small. I mean, I think you saw the largest files, like a few hundred megs. And most of the things that we're dealing with are a hundredth of that size. But our remote sensing pipeline has files in the gigabytes, and intermediate artifacts would presumably be the same. And we've talked to the company about some features around that. One of the things that we've discussed is this idea of making a compute space trade-off. So if they have all the provenance tracking that shows what needs to be done to create an intermediate artifact, then they should be able to run in a mode where they don't have to keep it, but you'd have to recompute it if you wanted it. And we think that would be a feasible approach to keeping that provenance tracking for our remote sensing pipelines without having crazy data growth, but it's not in the product yet.
Great. So while you're waiting for more questions, I have one more for both of you. So how Pegasus and also Pachyderm, on your perspective, Steve, handles like large workflows? Yeah, some of them, can be, as there was a slide from Ryan saying millions of jobs, So what is the strategy to handle this sort of workflows?
So I don't know how that would work in Pachyderm because we haven't done anything that large. I do know when you create pipeline specifications in Pachyderm behind the scenes creates a replication controller inside Kubernetes to manage the pods at the parallelism spec that you've said. So if you said a parallelism spec of 4, it'll make 4 replicas run. And then if your datum specification would make 1,000 datums off of one trigger, it would do 4 of those at a time in your 4 parallelism specification. And so it basically keeps the pod running and in a loop that just keeps running through the command that you've specified to go over all your data, and it just stays there waiting for more input, unless you set the pipeline specification to suspend, in which case when there's no work to be performed, it shuts down the containers and then starts another one. So in the context of what has to be running in the cluster, it wouldn't have to be millions of containers running in the cluster. It can just be pieces of the pipeline that can start and stop as needed for what's running. In terms of managing the depth, we've managed millions of files, I think that the file management is actually more where the overhead is in Pachyderm than the DAG management, because the DAG view is pretty much just viewed as these repos and this thing in a command as independent objects. So I wouldn't foresee a scaling issue going to that depth, but I'd be concerned about how large a cluster you would need to adequately run the DAG and how many objects you'd be tracking.
Yeah, so I guess in the case of Pegasus and like with regards to like the LIGO workflows, so the way that it's done is using, we have this notion of like hierarchical workflows. So you can sort of define a root workflow, and as you add jobs to it, those jobs themselves can be sort of like sub workflows. And that's what they do, because sort of their workflows get really large, and in order to your programs, your workflow scripts, to group them together, you can create like hierarchical workflows. And let me just try to share my screen here. I have a picture of what that looks like. Yeah, so in Pegasus, you can define this root workflow, and then you have these sub workflows, which to the root workflow, they just appear as jobs themselves. But that's the mechanism that we have in place to sort of do this organization. And it's also a way for us to create dynamic workflows as well. So, as one sub workflow can create some output, pass data to the next sub workflow that can be planned at the time when it is run. Yeah.
Great. So I'd like to thank you, both of you, for the great talk and different perspectives. And thank you, Wendy, for popping up and put already the advertisement for the next closing talk. So this time is just a 10 minutes break. So just a technical break, and we're gonna go back to the closing. We're gonna talk about the next steps that we really hope this is just a start of the discussion, that we keep, Slack alive and doing all of the discussions. See you in about 10 minutes, and thank you all.
Thank you.
Thanks, guys.